In this video, we will learn how to perform functional group interconversion from alkyl halides. Alkyl halides are wonderful substrate for substitution reaction, which then allow us to convert alkyl halide into other functional group. For an example, if we were to have an alkyl halide, by now choosing the proper nucleophile, we can then perform substitution reaction to convert this into another functional group of our interest. And here are some of the examples. So here in this case, alkyl halide will be the substrate, and now the leaving group will then be a halogen. By now choosing the proper nucleophile, for the first example, in this case, sodium acetate, and this entire component here is then our nucleophile. We'll be able to convert this substrate into an ester. And similarly, by choosing another nucleophile, we will be able to convert this into a nitrile or a thiol by using this as the nucleophile, or alcohol by using hydroxides as our nucleophile, and many other functional groups. But in order for us to get the right products, we have to follow certain guidelines to make sure that we have the optimum reactions in order to favor the product that we want. And the guidelines are as follows. First, analyze the substrate, and then the stereochemical outcome of what we want. So, look at the structure of the substrate and the product, and ask yourself this question: the reaction need to be stereospecific. If the answer is yes, we need this reaction to be stereospecific, so we can produce certain types of stereochemistry. If the answer is yes, then very likely we have to perform an SN2 reaction with our starting alkyl halide. If the answer to this is no, the reaction do not have to be stereospecific, then that when we can do both SN1 or SN2. And second, analyze the leaving group. Is the leaving group enough to leave on its own, or do it need to be protonated? In many alkyl halides, the halides are good leaving group, so therefore we know that we can perform chemical reaction on this. However, if we were to have another functional group that is not an alkyl halide, then it may need to be protonated. But we have to figure out whether the leaving group is good or not. And third, choose the condition that will favor the required reaction mechanism. First, pick your nucleophile. If we want to do an SN2 reaction, then we want to have a strong nucleophile. Whereas if we were to do an SN1 reaction, then we need to have a weak nucleophile. And second, the solvent. If we need to do an SN2 reaction, then we will then need to use an A product solvent. Whereas if we were to do an SN1, then we want to use a product solvent. So these are the aspects right here that we need to consider in order to select the optimum condition so we can make what we want. Let's now try an example. So in this case right here is the product that we want to make. We want to start from an alcohol and converting this into a nitrile. So how would we accomplish this following transformation? So in this case, again, this is not an alkyl halide, but if it's an alkyl halide, we would still employ the same strategy. So the first step is to analyze the substrate and the stereochemical outcome. So in this case, we have one stereochemistry in here, and on the product, it have the inverted stereochemical outcome. So we will then know that this reaction is stereospecific. So thus, we have to do an SN2 reaction in order to make the product that we want. And second, now analyze the leaving group. So here in this case, is the leaving group good on its own, or do it need to be protonated? And we have learned already that hydroxy group or alcohol, these are not good leaving group. So they have to be either be one, protonated, or second, convert into another functional group that would make it become a better leaving group, which is the tosylate group. So in this case right here, we will then see, since we are performing an SN2 reaction, for an SN2 reaction, we will then need to use tosyl chloride to convert this into a tosylate group. If we were to do an SN1 reaction, then that when we can protonate this. So in this case, since the reaction that we need to do to obtain the correct stereochemical outcome will then be an SN2. So that would then mean that we have to use the tosyl chloride to convert the hydroxy group into the tosylate group. And third, choose the condition that would favor the required mechanism. So here in this case right here, first our nucleophile. We will then see our nucleophile will then be the cyanide. Since that group is replacing the alcohol, and cyanide is a good nucleophile, and we want to perform an SN2 reaction. So this is the right nucleophile. And now to make it into an actual reagent, all we have to do is give it a cation. So in this case, we can use anything that is positive. We can use sodium, and now we will have the real reagent, sodium cyanide. And lastly, the solvent. The reaction that we want to perform is an SN2 reaction to produce the right stereochemical outcome. So therefore, to favor SN2, we have to use an A product solvent, such as DMSO. And now let's combine everything together. So again, we have seen already that the first step is to convert this into a tosylate group first. And that will be accomplished by taking this and reacting this with tosyl chloride in the presence of pyridine. And followed by the second step, using sodium cyanide in the presence of a polar A product solvent, DMSO. And that's how we'll be able to accomplish this transformation. And if we were to now write down the products of all of the steps, it would then be as follows. On the first step, when we take our starting material and reacting this with tosyl chloride, we would be able to convert this into a tosylate group. And now this entire group here, it now become a good nucleophile, a good leaving group. And the next step to then take this and react this with sodium cyanide in DMSO. The cyanide is our nucleophile. It then will come in and attack this carbon right here from the back side. And again, this is an SN2, so it attacks from the back of the leaving group and kicking that off. And now we'll be able to make our product. So there you go. That will be the products of after each of the steps. And finally, making the product of what we want. Let's now try a few additional problems. So in number 2, we want to take this substrate and convert this into an alcohol. So in this case right here, we will then see that we have an alkyl halide and we want to convert this into an alcohol. So that implies that we can do this by substitution reaction, in which our nucleophile is the hydroxy group. So in this case, let's now follow the step. First, analyze the substrate and the stereochemical outcome. So in this example right here, we have a primary substrate, and we know the primary substrate would favor SN2. So therefore, we can perform SN2 reaction to get the product. And also in this reaction right here, the product does not have any stereochemistry to it. So therefore, it does not matter whether we want to do SN1 or SN2. But because we have a primary substrate, it'd be best for us to use SN2. And now, let's now analyze the leaving group. So the leaving group is the iodine, which is a good leaving group. So therefore, we can have the leaving group check off, and we do not need to do anything to it. And third, in this case right here, the nucleophile. The nucleophile will then be hydroxide. So we'll have to use sodium hydroxide as our nucleophile. And lastly, because we are now want to do an SN2 reaction, we want to use a polar A product solvent such as DMSO. So combine all of this together, we can accomplish this in this one step by reacting this with sodium hydroxide in the presence of DMSO. And we will be able to make this product in this one step. And now the next example. So in this case right here, we want to convert this alcohol and convert this into an alkyl halide. So how we perform this transformation? So first, let's now analyze the structure of the substrate and the stereochemical outcome. So in this case right here, there's no stereochemical outcome that is required. But in this case right here, because this is not a chiral center, so therefore there's no stereochemical outcome that would be needed. So we can then perform either SN1 or SN2. But because the structure of the substrate is tertiary, and we know that tertiary substrate would be ideal for SN1, so therefore the chemical reaction that we would have to perform would then be an SN1 reaction. And now, next one, the leaving group. Hydroxy group is not a good leaving group, so it have to be protonated first. So in this case, we need to treat this with an acid. And third, the nucleophile. Our nucleophile would then be the bromide. And so that would then be ideal. So we can actually use HBr to provide both the proton to protonate our alcohol and have our bromide to act as the nucleophile as well. And lastly, the solvent. Well, in this case right here, we can have some water as the solvent, and that would still work. And in fact, that would be the reaction, how we would be able to accomplish this transformation. And now for number 4. So we want to convert an alcohol into an alkyl iodine. So how will we be able to accomplish this transformation? So here in this case again, let's analyze the substrate. So our substrate is primary, and the molecule don't have a chiral center on it. So therefore we can either do SN1 or SN2. But because we have a primary substrate, it would be best for us to use SN2. And second, analyze the leaving group. So in this case right here, to do SN2, the OH group is not a good leaving group. So therefore we have to convert this into a tosylate group first before we can do SN2 reaction on it. And next, the iodine would then be our nucleophile, because that is replacing the hydroxy group. And lastly, the solvent. In this case, because if we want to do an SN2 reaction, we will have to use a polar A product solvent. So the step would then be as follows. First, convert the hydroxy group into a good leaving group to do SN2, and that can be done by reacting this with tosyl chloride in the presence of pyridine. And then next, we will want to add our nucleophile with the iodine. So we can have sodium iodine, where the iodine would then be our nucleophile. And this is done in DMSO, a polar A product solvent. And that is how we will be able to accomplish this transformation. And for number 5, here in this case right here, let's now analyze the substrate and the stereochemical outcome. So in the product, we would then see that it have the inverted in the configuration. So that basically means that we have to perform an SN2 reaction. And in this case, our substrate is secondary, which basically means that we can also do SN2 as well. But in order to favor SN2, we have to have a good nucleophile, because secondary substrate can do both SN1 or SN2. So we have to somehow limit the possibility of SN1 by having a good nucleophile and second, an A product solvent. And now as for the leaving group, bromide is a good leaving group, so we have it checked off. And next, the nucleophile. In this case, our nucleophile would then be SH, and that will be our nucleophile. And lastly, the solvent will have to be an A product solvent. So this can be done as follows by taking this and reacting this with this reagent in the presence of DMSO. And we will be able to produce the product that we needed. And on number 6, again, by analyzing the structure of the substrate, we will then see that the product have the inverted in the configuration. So therefore, we have to again perform an SN2 reaction. And since this is a secondary substrate, we know that can either go both SN1 and SN2. But in this case, we have to do an SN2 in order to get the right or the correct stereochemical outcome. And now the nucleophile that what we need will then be this acetate. And the bromide is a good leaving group. So we will be able to accomplish this reaction as following. So this is our nucleophile. And now all we have to do is give it a cation, so that way it will become a real reagent that would exist. So sodium acetate, and in the presence of DMSO, to favor SN2 reaction. And that's how we will be able to accomplish this reaction in one step. And now, as for our number 7, so in this case right here, we have this stereochemistry, and on the product, it has the correct stereochemical outcome. Now again, the reaction here is stereospecific. We have to produce this stereochemistry. And if we were to remember this, in order to do this, we have to perform SN2 reaction if we have to have stereochemical control. And in this case right here, if we were to do only one substitution reaction, we will have the product have the inverted in the stereochemical outcome. So to get it back to the right stereochemical outcome, we have to perform 2 SN2 reaction. For an example, so here in this case right here, first we can do one substitution reaction by taking this, reacting this, let's say with sodium iodide in the presence of DMSO. And that will then give us the inverted in configuration. And now we would have the iodine in here. And next we will then perform another substitution reaction by taking this and reacting this with sodium acetate in another DMSO, and that will then give us the product that we want with our right stereochemical outcome. And if we were to now draw the product of each of these steps, when we perform the first reaction, we will be able to get this product. And now when we take this and treat with the second reagent, it will do another SN2 reaction. And now the product will then be inverted, and we end up with the right stereochemical outcome.